Good afternoon. This is Professor David J. De Los Reyes. My topic this afternoon will be an application problem of differential equation, okay, the growth of bacteria. It's a very interesting subject matter because we will be solving problems on the growth of bacteria using differential equation. So on my channel, the topic this afternoon will be the growth of bacteria using variable separable differential equation. Okay, I will try to read the problem. Under favorable conditions, the rate of growth of bacteria is proportional to their number. If a colony of bacteria increases from 1 million to 1.5 million in 1 hour, what will be their number after 24 hours? I think this is a practical problem for us today. We passed by the pandemic time. We are not yet over with the so-called pandemic time. So I think at least we know how to compute the population of a bacteria using differential equation. Okay, so this is now lesson number 15 on my course differential equation under the topic variable separable. And for this afternoon, I will now be giving you example on the computation of the growth of bacteria using variable separable differential equation. We are given the problem. The problem states that dn over dt is proportional to their number, where n is equal to the population. The problem states that the rate of growth of bacteria is proportional to their number at any given moment in time. We are given two initial conditions. At time t equal to 0, the population of the bacteria is 1 million. So it seems we are given a beaker over here, and the total number of bacteria inside the beaker, supposing we are inside the laboratory, the total number of bacteria initially was 1 million. And the problem says that after 1 hour, the total number of bacteria inside the container, assuming this is only for illustration purposes, it is 1.5 million. So the problem is asking, after time t equal to, sorry for this one, this should be 24 hours. After 24 hours, what will be the population or the number of bacteria inside the container? So this is just an illustration, and we could relate this to actual problems in real life. Okay? At time t equal to 0, the bacteria is 1 million. After 1 hour, it increases to 1.5 million. So after 24 hours, what will be the total number of bacteria inside? And the solution of this is actually of significance to us. This is now the importance of differential equation. Okay, let's try to bring out the solution. The given condition is that dn over the differential n over differential time is proportional to n. That's given in the problem. The rate of increase of the population with respect to time is proportional to the population at any given moment in time. So actually, we could bring out the required differential equation from this condition. Okay? dn over differential time is equal to kn. Okay? This is the differential equation. Let's separate the variables. There are only two variables. It's n and time. This k here is constant. Okay? So dn over n is equal to k dt. Okay? We separate the variables already. Okay? So to bring out the relation of population as a function of time, we will try to integrate. So the integral of differential n over n equal to the integral of k dt. We are now integrating. Okay. Luckily, on the left-hand side, it's an easy money, guys. This is just the integral of dn over n, and this should fall under natural logarithm. So this is natural logarithm of n equal to the integral of k dt will be k times t plus k1. Okay? This is natural logarithm. We will try to compute for n as a function of time, so we will try to eliminate this natural logarithm here. And to eliminate the natural logarithm, we will take the antilog of both sides. The antilog of a natural logarithm is by simply raising both sides of the equation to e. So e to the natural logarithm of n is equal to e raised to kt plus k1. And e raised to the natural logarithm of n will be just be simply n equal to. The right hand side will be the product of e to the kt times e to the q1. And we will let e to the q1 equal to k2. So the right hand side will be equal to k2 times e raised to kt. This is now our general solution. The general solution of the population of the bacteria as a function of time. There are two constant of integrations, k2 and the initial k here. So to derive the relation of n as a function of time with this value k2 and k known, we apply the initial conditions. At time t equals 0, n is equal to 1. 1 will be equal to k2 times e to the 0. Because k times 0 will be 0, and e to the 0 will be 1, so k2 will be equal to 1. Okay? Then at time t equal to 1 hour, n is actually 1.5 million. We'll go back here, therefore 1.5 equal to, the computed value of k2 is actually 1 times e raised to k times 1. So the unknown is actually right hand side, we rearrange, this will be e to the k equal to 1.5. The unknown k is actually on the exponent, so to bring it down, take the natural logarithm of both sides. The natural logarithm of e to the k equal to the natural logarithm of 1.5. And if we try to expand this one, we bring down the k, we could do that under laws of logarithm. K natural logarithm of a, but this is 1. Okay, therefore k now will be natural logarithm of 1.5. 1.5 is greater than 1, so the value is actually k is equal to 0.40546, positive. Therefore, n now as a function of time will go back here. We substitute values for k and k2, this should be 1 times e raised to 0.40546 times time. So actually we are now given n as a function of time. Okay? We derive the solution to our problem. So we will now apply the condition of the problem. The problem is, at time t is equal to 24 hours, what will be n? What will be the population of the bacteria after 24 hours? Obviously, it increases. Okay? So we use this equation, n now will be equal to e raised to 0.40546 times 24. N now will be equal to e. The product of this times 24 is 0.73104. 2.72 something raised to this. Use your calculator, guys. It is 6.32 millions. Obviously, the population of the bacteria after 24 hours increases to 6.832 millions. That is our answer. That is the significance of the differential equation in everyday real situations in our life. So actually, differential equation is very important. It is the basis of the solution to our problems in this world. Okay. Good afternoon, Los Angeles. That is the growth of bacteria, computation of the population, okay, after 24 hours. Okay. Good afternoon, Los Angeles.